Today's topic is magnetism. And of all the topics in physics, this is probably the most requested and early on in the course. A lot of students will come up to me and say, "Hey, are we going to study magnets? I really want to understand how magnets work." And to that, I usually say, "Yeah, we'll study them later, but good luck with that because it's really tricky, and the things that happen are usually written off as being relativistic distortions or um, quantum interactions and things like that. So you know that there's strange things going on at the super small, super fast level. So we'll start with the macro level. We all know that magnets have poles and that these poles can push or pull on things, and that's what the lab we're going to do will visualize. Like poles repel. In other words, if you take two north poles and try to push them together, they'll repel each other. And same with two south poles, but a north and a south will attract. And these poles always occur in pairs. Uh, they are looking for magnetic monopoles, yet to be found. But if you take a bar magnet and break it in two, you now have two smaller bar magnets. And then if you break that in two, you now have four smaller, and so on and so on and so on until you get down to an individual atom. And that atom would be a north-south magnet. Um, the magnetic fields extend out from one pole to the other. By convention, we say it runs from the North Pole to the South Pole. It varies with strength. It varies in strength with distance from the pole. So the further from the pole, the weaker it is. Um, and these magnetic fields can interact with each other. As these show, these are two bar magnets. The south and south are repelling, the north and the north are repelling, but the north is attracting the south. Um, and then here's two oppositely oriented bar magnets, and this is part of the lab we'll do as well. These are iron shavings that are just sprinkled in between the bar magnets, and then they just are allowed to line up within the fields. Okay, now where do these fields come from? Well, they come from charges, moving charges. So each charge has an electric field surrounding it. If it's moving, then those fields get distorted and become magnetic fields. That's where the special relativity comes in. Okay, so moving charges, especially if they're moving at super high speeds, induce electric fields. And within atoms, of course, we know that electrons are moving. They're moving within the orbitals, but they're moving randomly. And so their orbitals and their spin produce tiny atom-sized magnetic fields. But because the spins are random, in most atoms, these effects cancel out. So a normal atom is neutral electrically as well as neutral magnetically. But iron, as well as neodymium, nickel, and cadmium, but most pronounced in neodymium, but historically iron was the most known about. There's a couple of extra electrons because of their electron configurations. They have a couple of extra electrons that are quote unquote uncancelled, meaning they are north and south, and they are permanently so because of their spin mostly. So iron atoms are permanent north-south atom-sized magnets. Now, that's not going to be a strong enough influence to really do anything, especially if those atoms are aligned randomly. But because of that strong interaction, they line up together in clusters called magnetic domains, which are comprised of billions of iron atoms. So in ordinary iron atoms, these domains are randomly oriented, meaning here's a billion iron atoms that are oriented north-south this way, and then their neighbors are oriented this way, and then this way. So the net effect is that a just a bar of iron or a nail or something like that is going to be randomly unmagnetized because the domains are randomly oriented. But if it sits long enough in the Earth's magnetic field, or if it takes a long time for it to cool, like magnetite, it takes a long time for it to cool, so the magnetic domains can be lined up during the cooling process, so that ore is itself magnetic. Or with uh, permanent bar magnets, they can uh, introduce the bar to a strong magnetic field and align the domains strongly so that it becomes a strong, quote unquote, permanent bar magnet with a north south that are strongly magnetized. Now, what about the induction of a magnetic field from current? So we know that moving charges induce magnetic fields. If we have those moving charges causing a current to flow through a wire, so here's a wire with current flowing, and you notice that the compasses are all pointed north-south. Now, when the current is caused to flow through the wire, notice that the compasses are now aligned in a circular pattern because there's a magnetic field surrounding that 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 wire. Now, here's some iron filings with a current carrying wire, and the magnetic field is circularly around it. Now, we're going to learn in a second how to figure out what the direction of the field is using what's called the right-hand rule. If you take the wire like this and you know what direction the current is flowing, that would be your thumb, and then the direction of your fingers relative to your thumb is the direction of the current, and then the force field that's produced by that current is perpendicular to that. Okay, so you have this current bearing wire and the magnetic field is in this direction. If you coil the wire, you can see that the field strength is going to be stronger inside this coil with the current running through the wire. Now, in order for the current not to jump this gap, this wire has to be insulated. And usually you want a thin coating of insulation so that the current can go through, but the magnetic field isn't itself blocked. Now, the more loops you have, you can see the strength of the magnetic field here is greater than out here, but with a number of loops, it's greater still. So that's the essence of what happens with magnetic motors and generators, is that they have a bunch of coiled wire, and then they move magnets relative to this, or they run a current through it and induce a magnetic field relative to that. Okay, so the direction of deflection, and this is Faraday's equation that tells you how to calculate the strength of the force field. We're not going to concern ourselves with that, but I show you this diagram just to show you that if you have like an electron beam moving through a magnetic field, its direction is perpendicular to the beam. And similarly, if you have a current electric charge running through a current bearing wire, notice that when the north-south field is directed in this way, the force is up, and if it's the current's running the other way, then the force would be down. Or if you turn the magnet with the current running this way, and you turn the magnet around, then the force would be opposite also. Okay, so there's a diagram of the right-hand rule. I learned it where the current was the thumb, and then the force was this way. But just remember, everything's perpendicular to each other. Okay, so here's how I learned it. And then the force would be out this way. Okay, so meters and motors. So the way an electric meter, like a multimeter that can measure amps or current or voltage, it has coils, and then this would be a piece of iron or a magnet, bar magnet, and then the current, direction of the current and the strength of the current would deflect that magnet. Okay. Now, if it's caused to move, and then the current interrupts, and then as it comes around, it's caused to move again and again and again and again, and then progressively gets faster and faster. You no longer have a meter, you now have a motor. So the first electric motor built was designed this way, and we're going to replicate this in the next lab we're going to do. So there's current running through this wire, and then this was mercury, and then there was a bar magnet here, and the wire started to spin around the bar magnet. We're also going to make one like this, where the current is running through the wire, running through this what's called armature, just a bunch of coils, and then out the other end. So there's a magnetic field inside and out of this magnet, and it's oriented in a certain direction. If the current gets interrupted, then it pushes the armature, and then it coasts, and momentum carries it around to get pushed again and again and again and again and again, and starts spinning faster and faster. And this is a permanent bar magnet. So the interaction of the temporary magnetic field of this armature and the permanent magnetic field of this magnet is what caused the motor to spin.